Hi, I'm Andrew Adams. I'm one of the creators of Halide, and this video is a demonstration of how I use Halide in my day-to-day job to make image processing code go fast. Now, a lot of the tools I'm going to be using and the things that I'm going to do aren't going to make any sense to you if you haven't already done the Halide tutorials. So I recommend, if you haven't, you go do those first and then come back to this video. Okay, so here's a piece of Halide code that was someone posted on GitHub on the Halide project and asked for help scheduling. It's a very straightforward blur. So if we look at this, we include the Halide header, we use the Halide namespace, we define this generator class, and a generator is the unit of Halide code that you use when you're doing ahead of time compiled Halide, which is what most companies do. We have an input that's uint8 two-dimensional and an output that's the same. And then we have a generate method that actually defines the algorithm. So we declare some variables, we add a boundary condition to the input, we upcast to 16-bit, we blur in X, we blur in Y, and then we downcast the result back to 8-bit. Okay, so this code currently has no schedule at all, so it will by default aggressively inline everything into the output. For a lot of algorithms, that will take the age of the universe to compile. But for this one, it's fine. Fully inlining everything is actually a reasonable choice here. So we'll just proceed and compile this and see how it works. Okay, so what do I have in this directory? Nothing else. Let's compile this blur generator file. Okay, so we need to point it to a Halide distribution. I have one freshly built over here. Okay, now I need to link it to libhalide, because libhalide is the compiler. Oh, we don't have an int main. So these generators need a sort of stub int main to get them going and to actually serve as the entry point to the binary. That is in tools, it's called gen. Okay, so now we have a compiled generator. It can't find libhalide.h. You could set LD library path. I like to use rpath to just tell it where to look. Okay, we have a generator. Let's not call it a.out though. I'll make a bin directory. I'll call it blur generator. Okay, so what can I do with this compiled generator? Well, there's one generator object inside it, and I want to select that one. -o must always be specified. I want to specify where the outputs go. Target is missing, and I have to specify what target I'm compiling for. I'm going to use x86-64 Linux AVX2. Okay, that seemed to work. Let's have a look in the bin directory. We have a static library with the compiled code. We have a blur.h, and we have this registration file, which will be useful later. Let's have a look at blur.h. Okay, so we have some forward declarations. We have our buffer type. We have a metadata type, we have some macros, then we have the actual function, the entry point to the function. It takes an input buffer and it produces an output buffer. We also have an entry point where you can call it with a void ** array, and that helps for cases where you don't statically know the type of the function. And then we have this metadata helper, which returns information about the inputs and the outputs. And again, that's so you can do some introspection at runtime. So at this point, we could define a little runner program to call this, test it, and benchmark it. But those all look pretty similar to each other. So we actually have a pre-canned one called runGenMain that uses the metadata to figure out how to run your filter. So let's use runGenMain. That's also in tools, runGenMain. And we will compile it against our blur, and we also need to compile it against this registration file. -o, and I will produce blur.rungen. Oh, okay, need an include. Okay, that runner is capable of doing things like loading and saving PNGs, so we need to link it to libpng, libjpeg, zlib, probably pthreads, and dl. I think that's the full set of libraries. Okay, so let's see what that looks like. Blur.rungen. Okay, we have a usage message. So the basic usage of rungen, or one of these rungen binaries, is you say, using the names defined in your generator, so input and result, you say input equals some file name, which I guess I don't have right now. So let's go get a grayscale file. Okay, so I think that's a picture of a parrot. So the input is some file name, and the result is, should be a slightly blurry parrot, I guess. Okay, and let's just quickly take a look at those two pictures. Okay, so this is probably going to be hard to see in the video, but if I flick between, this is the input, this is the output. To my eyes, yes, the output has been slightly blurred, probably invisible in the video, but it appears to be blurring the image. You'll have to take my word for it. Okay, so with the rungen, we can also do basic benchmarking. So we can say benchmarks all, and then you can set the amount of time that you want it to spend. Let's say 1 second is probably fine. Okay, so we have a runtime in seconds, and we also have a throughput in megapixels per second. So actually what I'm going to do is just to make the video a little bit simpler, I'm going to use machine parsable output, and I'm just going to grep out the milliseconds per iteration. Okay, 2.1 milliseconds is how long our pipeline currently takes. All right, let's write a schedule and see if we can make that better. Okay, so the first thing I'm going to do, which is almost certainly not going to make it better, is compute root everything. The output is implicitly compute root, but I'm going to make it explicit. And let's see. Now would probably be a good time to have an actual Makefile or something. So let's set our Halide to be okay. And to make the generator binary, where was it? It was this command line. Okay, and that depends on blur generator.cpp. Okay, and you could have a terser makefile by using some of the magic variables, but I'm just going to leave it like this for now. Okay, we also need a rule to make our blur.rungen, and that's going to depend on blur.a, and then we need a rule to make blur.a, and that's going to depend on the blur generator binary. So it's a multi-stage compilation here. Okay, so to produce blur.a we needed to run the generator binary, so where was that? It was this command line. Okay, and then to build rungen, that was the one where we referred to rungen main. Okay, and I'll define a phony test target to actually run rungen main. So that was that's the one I wanted. Okay, so let's see if that works. I'll probably okay, we're compiling the generator, we're running the generator, we're compiling rungen main, and we're benchmarking, and 9 milliseconds per iteration. So I think we started at 2 milliseconds per iteration, so we've successfully made it a whole lot slower. So let's leave some notes in here. Inline everything was about 2 milliseconds per iteration. Compute root everything was 9 milliseconds per iteration. Closer to 10. Okay, so how do we go about improving this? There are some extra outputs I like to turn on in the generator to help me understand what code is being generated. And to do that, you use the -e flag. So what I want is a static library. I want this registration file so I can use rungen main. I don't actually need the header for what I'm doing. And I want 2 additional outputs. I want some pseudocode that shows me what the compiled code looks like. That's called a statement file, STMT. And I also want to see the assembly. All right. Okay, so now in bin there should be a few extra files. blur.stmt. Okay, so this is pseudocode for what our current schedule is doing. So the start of the pipeline is all sorts of boring asserts and things like that. Then we actually get into the code. So our first func is called repeat edge. This is the boundary condition, and it is the width of the input plus 2 times the height of the input plus 2, or the output rather. So that makes sense. It gets a whole bunch of loop nests. There are 5 loop nests here for repeat edge. And that's because it's handling the edge cases in separate loops. So this is the top of the image. That's the left edge of the middle of the image. That's the actual steady state. So in the steady state, it's just a mem copy. And then there's the right edge, and then the bottom edge. Okay. So this is called, in Halide, it's called loop partitioning. Other systems call it index set splitting. But any func that has a boundary condition or has had a boundary condition inlined into it is going to be split up in this way. Then we have F0, F1, F2. Okay, those aren't useful names. If we change the Makefile to include debugging symbols in our generator, then Halide will do a little bit of introspection to figure out what those functions should be named. Okay, let's load the statement file again. Reread from disk. Okay, so now we have blur x, blur y, and result. Okay. Yep, so we have a separate loop nest for each because everything's compute root. Okay, let's start fusing things. Okay, I'm going to worry about parallelism last, and I'm going to start just by fusing things, and then I'm going to vectorize, and then I'm going to parallelize. So, the boundary condition and the upcast to 16-bit probably don't need to be done separately. So I'm just going to inline the boundary condition into the upcast. The cast back to 8-bit can probably be done immediately after the blur NY. There's no reason to do it as a separate pass, so I'm just going to inline the blur NY into that cast. Let's see where that gets us. (7.2 milliseconds). Okay. So now we have a loop nest for input 16, which is the upcast. We have a loop nest for the blur and X, and then we have a loop nest for the blur and Y and the downcast. Okay. So I can probably get better locality still if I compute these two things at tiles of the output. So let's do some tiling next. Let's make new variables to refer to the insides of the tiles. And I always have the best luck with 256 by 32 tiles for this sort of code. Not sure why. So I'm going to start there and we can try tweaking them later. Okay. And then often it helps to write the schedule in reverse order to the algorithm, because you're scheduling everything relative to the consumers of that stage. So you want to know the schedule of the consumer before you write the schedule of the producer. So let's compute blur X at tiles, which is X now. And we'll also compute this at tiles of the results. (1.4). Okay, so we're better than inlining everything. So we're probably onto something here. Before we start tweaking the tile size, let's just turn on vectorization. Let's see. We're using 8-bit and 16-bit values here. We're using AVX2. What is that? Let's try 32. I think that's right for the 8-bit values. You know what, I'm just going to make this a constant so that I can tweak it later. Normally you want to use the native vector width, but not always. Sometimes using wider or narrower can do better. Okay. (1.6). That's actually worse. Okay, so what's probably happening is that LLVM was already auto-vectorizing the code and doing a better job than we are. Yeah, 1.6, look at that. We could try different vector sizes. (1.6). (1.6). Alright, so we can confirm that hypothesis by turning off vectorization, quickly testing again. And now let's just run it under perf. Yeah, this is vector code. LLVM has done a really good job at auto-vectorizing this code already. So our explicit vectorization didn't add a whole lot. Looks like it's been... let's see. So the division by 3 in the algorithm is turned into a multiply and then a shift in 32-bit. And there are quite a few of those to compute a single vector of this. And this is a tail case, it looks like. Okay. The other way we can confirm that is by leaving vectorization off in the schedule and disabling LVM's loop optimization. Yeah, so LVM was just doing a really good job at auto-vectorizing the loop. So I find that the scheduling process makes more sense if I don't let LVM auto-vectorize, at least while I'm scheduling, and then you turn it back on at the end to see if it makes a positive difference or not. So for now, let's just proceed with Halide vectorization. .6, and we'll see if we can continue from here. Let's have a look at the statement file again. Okay. So we have a single result.y, result.x outer loop over tiles. Then we allocate a 258 by 34, which is 256 by 32 plus 2 in each dimension, buffer for the upcast input. Then we do the blur in x. Then we do the blur in y and the downcast. And there are multiple copies of this entire loop over tiles because we have separate ones for the tiles near the edges of the image and the tiles in the middle, because of that loop partitioning thing. So this looks like the case where when we're in the steady state in the middle of the image, because we're just loading a vector of the input, casting it, and storing it to a vector of input 16. Then we have our blur in x into a similarly sized buffer. Then we have our blur in y. Okay, so one thing I'm noticing is that we have this little tail vector. Because 258 isn't a multiple of our vector size, we have a little tail case to handle. We could potentially clean that up using a different tail handling strategy. I doubt it will make a difference, but it's worth a try. There's a boundary condition anyway, so we can just, instead of computing 258 values, we'll compute 256 values plus a whole nother 32. Yeah, that doesn't matter at all. All right. The scheduling process is, you form hypotheses, most of them turn out to not matter. Some of them turn out to be disastrously wrong, some of them turn out to work really well. Okay, so the next thing I want to do is, I think, take advantage of some sliding windows stuff. I don't have to compute the whole blur in x before any of the blur in y. I can compute it slightly lazily, just sort of one scan line ahead of when the blur in y is going to need it. So I'll store it at that site, but I'll compute it per scan line of the blur in y. The blur in y has been inlined into the result, so really it's per this yi coordinate of the result. A little bit faster. We can probably do the same thing with this. little bit slower, really. Huh. I wonder if we should be doing the upcast there, or if we should be storing 8-bit values, loading them as 8-bit, and then upcasting to 16-bit. Or maybe we should just inline the boundary condition and partition the loop that does the blur and X instead. Let's try that first. No, that's worse. That's much worse. Okay, now let's try just loading it as 8-bit and deferring the cast to uint 16 to the inside of the blur and X. Oh, clamped doesn't have XY coordinates. Clamp uses _0, _1, and so on. .4. Okay, progress. That was a better idea. I guess one option we didn't try was this, though. Just pre-computing a padded thing in 8-bit. Nope, worse. I guess we could also just compute it at blur in X's Y coordinate. .46. It means basically the same thing, I think. Let's have a look at the statement file. Okay, so we have, oh boy, tiles of the results. First we deal with the boundary condition. That's here. Then we do the, I see, tiles of the results. So for Y tile, for X tile, then scan lines within that tile produce one scan line of blur in X, and then for each scan line of blur in X, we first pad out that input scan line and then blur it. And the coordinate, the Y coordinate that we write into is this thing modulo 4, because blur in X is now stored in a circular buffer. Allocate blur in X, 256 by 4. We could make that explicit in the schedule if we like with the fold storage directive, but it's automatic. Okay. How are we doing in terms of throughput? Two and a half gigapixels per second. All right. So maybe now is a good time to turn on parallelism. We could do tiles in parallel. We could do rows of tiles in parallel. Let's try rows of tiles in parallel first. So blur X and clamped are inside the results parallel loop over rows of tiles, so there's no reason to parallelize these guys as well. 0.3 milliseconds, 0.38 milliseconds. Pretty good. What is that in terms of throughput? Ten gigapixels per second. Yeah. So this is at 32 threads. I have a 16-core CPU with 32 hardware threads. For some workloads, hyperthreading is bad though, so let's just try it with hyperthreading off by limiting Halide to 16 threads. Oh yeah, that's much better. 23 gigapixels per second. Okay. Okay, let's just set our, let's just keep that in mind and we'll keep testing both 32 and 16. Okay, what should we try now? Sometimes it's worth going back and looking at the algorithm and seeing if there are algorithmic changes you can make to improve things. In this case, we're dividing by 3 and quantizing, because that's division, integer division, rounding down. And then we divide by 3 again. We can do fewer divisions if we just divide once by 9 at the end. Okay, 0.39. And it's 16 threads, 0.157. And no real difference. So if you reduce the amount of compute and there's no real difference to the runtime, that usually means we're memory bandwidth bound. So could be interesting to try differently sized inputs then. So what I'm going to do is I'm going to load the Makefile, and instead of using just this grayscale 5 megapixel parrot, I'm going to use a synthetic input. Let's say it's 2000 by 2000. Oh, now we really want throughput though, because we're changing the size of the image. Grep throughput. Okay, so for a smaller image, we're getting 22 gigapixels per second. Smaller still, and I guess things like threading overhead start to dominate. Let's go larger. $27, all right. $32 gigapixels per second. Okay, so once we go a little bit larger, it is worth using those hyperthreads, and you get more total bandwidth. So I think what's happening now is we're really looking at properties of the memory subsystem and the memory controller. And if you had more work available in this pipeline, if there are other things you could fuse into it, then you should, because we're limited by the memory subsystem at this point. So I don't know, let's take our fastest configuration and see if we can make that any faster. Should the tiles be taller? Just set things to our fastest configuration. Okay. No, they should not. Should they be shorter? That was about the same. Okay, so making them shorter actually does a little bit more work, but it also creates more parallel tasks. So another option would be to make the x-coordinate parallel as well, to make more work. So now the tiles are done in parallel instead of rows of tiles. No, that is a terrible idea. Okay. Let's try making the tiles wider and shorter. 34. Is that the best we've seen? I think that's the best we've seen. 34 gigapixels per second. We could go wider still. .1024 isn't really a great divisor of 4000, but if you know exactly what the size of your output is going to be, then you can pick tile sizes that divide it evenly. 28, no, so that's too wide. Okay, let's try for values in between 32 and 16. $35. $34. Yeah, at this point we're really looking for a sweet spot in the memory subsystem. Let's make sure that the time is being spent where we think it should be with perf. Okay, that looks like a boundary case. Let's see, we have add, mul high unsigned word, and then a shift, so that's our division. So this must be the blur in Y, because that's where our division takes place. Here's another hot loop. Right? This is interesting. There's a call to memcopy. Now, this call to memcopy is in fact this func. LLVM has recognized that clamped in the steady state is just a memcopy and has replaced it with a call to memcopy. That's not always a great thing for LLVM to do, especially because of this V0 upper. But that is what it is for now. We could foil that by changing this back to input 16. Oh, I'm changing that back to X. Because LLVM will peephole recognize the boundary condition as a memcopy, but it won't recognize the boundary condition and upcast. 36. I think that's the best we've seen. Yeah, that's the best we've seen. Alright, 36 gigapixels per second. Not bad. I really feel like the tiles should be taller, so I'm just going to test that one more time. Nope. We could test wider vectors, but I think we're just about converged here. Yeah, wider vectors are about the same, just unrolls. .32. Yeah, no, we definitely want to use vectors of width 32. Okay, so how are we relative to where we started? So compute root everything, which would be like an unoptimized image processing library, was 10 milliseconds. Inlining everything with full fusion was 2 milliseconds. This was on the parrot image. I don't want perf. On the parent image, we're at 0.2 milliseconds. So we are 10 times faster than the default schedule, and a lot faster than an image processing library. Let's check 16 threads again. Slightly faster still. It's about 0.19 milliseconds. All right, I'm going to call it there. Thanks for watching.